All right, welcome to episode 26, and in this episode we are going to continue working on the display controller, and specifically we are going to work on a mechanism that will allow us to send commands and data to the display controller from the host system. Although it's not really going to be the host system, we are actually just going to use an Arduino in our prototype as a proxy for the host system. There are two main issues that we'll need to deal with. One is logic level conversion. So our display controller is an FPGA that uses 3.3 volt logic. Our host system is a 5 volt system that uses 5 volt logic. So we'll need to translate the 5 volt signals coming from the host system to the 3.3 volt signals that the FPGA needs. The 74LVC245 bus transceiver chip is ideal for doing that conversion. So we'll show how to do that in a little bit. The other issue is timing buffering of the data that the host system is sending to the FPGA. The host system will want to send commands at more or less arbitrary times, and the display controller may or may not be able to handle that data right away, so we would like to have a way that we can essentially queue that data so that the display controller can deal with it at an opportune time. FIFO memory chips, I think, are going to be a very nice solution to that problem. So what I would like to do in this episode is build a little prototype where we use an Arduino to essentially serve as a proxy for the host system. It sends commands to the display controller, and the display controller accepts and interprets those commands in order to control the color of the pixels that are generated on the display. Basically, every pixel will be the same color, and in some sense, what we will have done is implemented a 1:1 resolution frame buffer. So granted that this is a very limited start to our display controller, but nonetheless, it does give us a really essential component of the display controller, which is the ability to receive commands and data from the host system. Okay, let's get started. All right, so here is a 74LVC245 bus transceiver, and it's like any bus transceiver. It has a set of A pins, it has a set of B pins. There's a direction pin, and depending on whether we send a high or low value to the direction pin, it either copies data from A to B or copies data from B to A. And you may recall that we used 748CT245 chips to buffer our data bus and address bus in the host system, and this is, pretty much the same function. However, this chip is going to be powered from 3.3 volts, so it's basically a 3.3 volt device. However, its inputs are 5 volt tolerant, so we can basically send it 5 volt signals and it will translate them to become 3.3 volt signals. So basically the way that we will use this is that we will send it 5 volt signals from the host system, and it will translate them to 3.3 volt signals that can then be sent to the FPGA, and we will know that those signals won't damage the inputs of the FPGA. Note that we are more or less not going to need translation in the other direction, where the FPGA sends signals in the direction of the host system. For now, the only outputs from the FPGA that we will need to feed to a 5 volt device will be going to the FIFO memory chip. It requires only 2 volts to indicate a logic high, and the FPGA's 3.3 volts can easily meet that minimum, so it may be the case that we need to do some level conversion in the other direction later on, but for now we shouldn't need to. All right, so let me show you a little test circuit I made for this device, and there were basically two things I wanted to test. One is I wasn't that confident that my soldering was actually successful. This is an SSOP device, and it has a pretty fine pitch. But the other thing I wanted to check was just to confirm that my mental model for how this chip works was actually accurate. So let me show you the test circuit, and we will see that this thing does actually work. All right, so here's our test setup. So this dip switch here, normally the nodes on this side of the dip switch are pulled to ground via this resistor network, but when the switches are turned on, they are connected to 5 volts that is coming from one rail of a dual output power supply, and then the 5 volt signals come to the A side of the bus transceiver, which is powered from 3.3 volts, also coming from the other output of the dual output power supply. And so essentially we should see these 5 volt signals here being translated into 3.3 signals here. And I'm just using this resistor network and some LEDs just to see the individual output switch on. All right, so let's see if we can engage these dip switches, and we should see the LEDs coming on. So basically, as each one comes on, we're getting some confidence that the signals are correctly propagating from the 5 volt side to the 3.3 volt side. So I have measured the voltages with a multimeter, and they are actually correct. We are getting 3.3 volt outputs here. So I would say this is good confidence that our approach for level conversion is working. All right, so now let's think about and discuss how we are going to allow the host system to send commands and data to the FPGA. Now let's look at our circuit. The VGA output is essentially the same as it was previously in episode 21. Red, green, and blue color signals are generated by feeding 4-bit digital outputs through a resistor DAC. One change is that the resistor values have been modified so that the DAC produces color voltages in the range from 0 to 0.7 volts. The previous version of the DAC produced color voltages slightly greater than 0.7 volts, which can cause bright colors to be oversaturated on some displays. The new part of the prototype circuit starts with an Arduino Nano, which is a proxy for the 6809 host system. It generates 8-bit output data values on the host data bus D0 through D7, as well as an active-low write signal and an active-low reset signal. The data bus signals and the write signal are fed to an IDT7202 FIFO memory chip, allowing the host system to write 1-byte data values into the FIFO. The reset signal is fed to the FIFO clear input so that the FIFO is cleared when reset is asserted. The write signal is fed to the FIFO write input, so when asserted, the data value present on the data bus lines is written into the FIFO's memory. For the FPGA to be aware of commands sent by the host system, it needs to be able to read them from the FIFO. The FIFO's empty flag signal is sent through a 74 LVC245 level converter to an input pin on the FPGA. This level converter also converts the host reset signal to 3.3 volts so that it can be used safely by the FPGA. When the FPGA sees that the FIFO is not empty, meaning that a byte of data is available, it asserts the FIFO's read input. The FIFO then outputs the data value on its output pins, which are sent through another 74 LVC245 level converter to 8 input pins on the FPGA. Alright, so here's our first test circuit. So here's the Arduino. I have it programmed so that it will generate a reset pulse when it powers on. There's also a manual push button which will also generate a reset signal. So that comes from this pin on the Arduino to the level converter, comes out here into an input pin on the FPGA. So I've also reprogrammed the FPGA so that it accepts a reset signal and essentially resets all of its internal state to an essentially inactive condition when reset is asserted. So essentially what we should see when I hook this up to the VGA monitor is that when reset is asserted by the Arduino, the display basically will show nothing, but then when reset is deasserted, we should see the test pattern. So let's see, yeah, fingers crossed, let's see if this works. All right, so it took a lot of messing around, but I think I have it working. So here's the Arduino, and it's generating a reset signal, which I can control using this push button. So when I press it, reset is asserted, the FPGA detects that reset is asserted, it resets its internal state, so it stops generating sync and pixel values. When I release reset, there's a delay, and then when reset is deasserted, the FPGA essentially initializes and starts outputting a display signal again. So yeah, I think we're in good shape. So I'm going to now continue to build more of the circuit. So I think we are ready to add the FIFO and actually try to send data to the FPGA. All right, we have some cat activity on the bench. All right, so I have wired up the entire circuit. So here's the FIFO chip, here's the other level converter. Everything's connected according to the schematic. I've verified it using the multimeter in continuity mode. So I think we're ready to test. The first thing I want to do is to enable all of the pins, the additional pins on the FPGA board that are going to be connected, and make sure that it still at least generates a video signal. I found that Verilog, at least the way that I'm using it, it just seems to be very sensitive to tiny changes, causing the entire thing not to work for unexplained reason. I guess this is just the nature of FPGA programming. So, all right, let's see if we can get this to generate a signal again. Well, somewhat unexpectedly, it seems to work. I have all of the pins that are being used for input and output on the FPGA programmed into the design. Right now, it's just reading input and not doing anything with it, but the test pattern still works. Reset detection still works, so this is a good sign. All right, so the last step is to now have the FPGA actually try to read commands from the FIFO. Here is the state machine I designed to allow the FPGA to read commands from the FIFO. But first, let's talk about clocks. You may recall from episode 21 that I generated the 40 MHz dot clock timing for the 800 by 600 FPGA signal by driving the FPGA logic at 240 MHz and dividing by 6. I found through experimentation that my FPGA logic worked more reliably when I lowered the internal clock frequency. So the internal clock signal now has a frequency of 159 MHz, which is the closest I could get to 160 MHz using the FPGA's PLL. Dividing this by 4 yields a dot clock of 39.75 MHz, which is close enough to 40 MHz that we can still generate an almost within spec 800 by 600 FPGA signal. The state machine for reading commands from the FIFO uses the same tick counter that the video signal generator uses to generate its pixel and sync signals. Driven by the FPGA's internal 159 MHz clock, the tick counter counts from 0 to 3 repeatedly. Each tick represents about 6.25 nanoseconds, and 4 ticks represents about 25 nanoseconds. The state machine starts in the ready state. When the tick counter is 0 and the FPGA sees that the FIFO's empty flag is not asserted, meaning that the FIFO has a byte of data available, we assert the FIFO's active low read input and move to the wait for data state. Note that because the tick counter is incremented on each clock cycle, when the state machine reaches the wait for data state, the tick counter will have the value 1. Once the tick counter reaches 0 again, we move to the data ready state. Again, because the tick counter is changing, it will contain the value 1. In this state, when the tick counter equals 2, the FPGA latches the data available on the FIFO's data output pins and transitions to the done with read state. Because a total of 6 ticks have elapsed, we have waited for 37.5 nanoseconds since asserting the FIFO's read input. Because we are using a 25 nanosecond FIFO, this should be plenty of time for the data to have stabilized. From the done with read state, when the tick counter is 3, which will be true immediately, we deassert the FIFO's read input and return to the ready state. According to the IDT7202 datasheet, the data should continue to be valid for 5 nanoseconds after deasserting the FIFO's read input, so we shouldn't have any problems with the FPGA's hold time when latching the FIFO data. Each time a byte of data is read, it is saved in an internal 1-byte FIFO. At this point, the value can be used by other logic within the FPGA. Okay, so in theory, the Arduino is sending commands to the FIFO, and the FPGA is, as far as I know, reading commands from the FIFO. The FPGA isn't doing anything with them. However, the test pattern generation still works, the reset still works, so the FPGA design does appear to still be working. So I think what I will do next is I will use the oscilloscope to see if I can capture the Arduino asserting the FIFO write signal, followed by the FPGA asserting the FIFO read signal. So let's give that a try. Alright, so here's channel 1. This is the Arduino writing to the FIFO. It's the FIFO's write signal. So if we single shot triggering on a falling edge, we do get a nice write pulse. So I'm pretty sure that the Arduino is writing to the FIFO. Alright, so here's the problem. If we trigger on the Arduino writing to the FIFO, everything seems to be fine. However, on the second channel here, this is the FPGA reading from the FIFO, and it's asserting the read input on the FIFO more or less constantly. So clearly, the logic in the FPGA is not working correctly to detect when the FIFO has data available. Alright, so this is something I need to investigate. Alright, so I think what the problem was is that I had pin 23 disconnected here. This turns out to be an input, and it actually has 2 functions, one of which has to do with putting the FIFO in expansion mode. If you want to create a FIFO that's wider than 9 bits, you can basically drive multiple of them in parallel. But in single device mode, it acts as a retransmit input. And so I think what was happening here is that the empty flag was never being deasserted because the FIFO thought that it was constantly being asked to retransmit the data value that was already present. And so because the empty flag was never deasserted, the FPGA tried to read data from the FIFO continuously, explaining the behavior that we saw. So the solution here is pretty easy. We just need to connect this to logic high to disable it. And I did confirm that when I made that change to the circuit, the empty flag did behave as expected. So yeah, fingers crossed, I think we are potentially ready to read some data. All right, so I need to work on my test setup some more and restore the functionality that allows the Arduino to send multiple data values and the FPGA to read multiple data values. All right, so let's see if we can get that to work. All right, so I've done quite a bit of experimentation and work on the FPGA design, and I think I have the FPGA reading data from the FIFO reliably. So basically what we're seeing here, same setup as before. This is the FIFO read signal. This is the write signal that's coming from the Arduino. This is the empty flag. And it's triggering repeatedly because I have the Arduino writing relatively frequently, I think like 4 or 8 times a second. So if I single shot, we see what we expect to see. At the end of the Arduino read pulse, the empty flag is deasserted because there's data available, and the FPGA immediately reads it. And we can do that as often as we like. And it works every time, as far as I can tell. And I have my multimeter set up to monitor the full flag on the FIFO, and it is always deasserted, so that implies that the FIFO is not filling up. The FPGA is consuming data from it basically continuously, so that's exactly what we want to see. So I think I'm actually ready at this point to have the FPGA actually start using data that's received from the FIFO in order to control what's on the display. So, all right, let's see if we can set up an experiment to do that. All right, so I apologize for the very garish video display here, but essentially what's happening is that the blue pixel values are being chosen based on the data values that are being sent by the Arduino, which are just increasing count values, and so we get this sort of flashing effect. But in any case, this is definitely good progress. The FPGA is displaying stuff that is based on data that it is receiving from the Arduino, so that's a really good milestone to have reached. I still need to work on the Verilog code. I'm still not entirely satisfied with how things work, and it's still a bit unreliable and flaky, but I'm going to keep working on it. The final experiment for this video will be, I would like to control each of the red, green, and blue component values independently and have a way of sort of selecting them interactively. So I think that's going to be the last thing that we do. Let's see if we can make that work. All right, so last experiment, I have these 3 trim pots hooked up to the Arduino using the analog inputs, and basically this one will control red, this one controls green, this one controls blue. So as I adjust these, the Arduino sends commands to the FIFO, which in turn are read by the FPGA, and that controls the color of the generated pixels. So took quite a bit of doing, but it seems to be working finally. One thing that I changed is I'm now clocking the FPGA at 120 megahertz instead of 160. So it seems that timing issues internal to the design are going to be a big issue going forward. So I think as I learn more about Verilog and FPGA design, eventually I'll get a handle on that. And even if the FPGA internally is running at 120 megahertz, I think that should be plenty fast to generate a text mode. I'm hopeful anyway. So finally, I think we are at a successful conclusion to this episode. All right, well, thank you for watching to the end of this video. So what I learned is that FPGAs are hard, really hard. The good thing is I learned a lot in this experience. Even getting this little bit of functionality working was a good experience and did make me more comfortable with Verilog and digital design. So I think that is hopefully knowledge that will be useful going forward. The next step is to start to use the internal RAM resources on the FPGA. So there are block RAMs, there is a larger single-ported RAM, and this will be used to store font data, palette data, and character and attribute data. And once that data is in the memory, then we can start trying to generate some characters. So that's the next step. As always, I have linked the resources, including the schematics and code, from the video description, so look below for those things. And thanks again, and I will see you in the next video.